Now, in a couple of lectures down the line, we will discuss runtime complexity and memory complexity. When we do that, we will figure out that Quicksort has an average runtime complexity of order of n log n and a worst case time complexity of order of n squared. But hold on to your horses. There are still a couple of lectures before we actually discuss how this is derived. Okay. Now we are going to discuss MergeSort. Now, before I move on to MergeSort, any questions on Quicksort? Eric is asking, it seems to have a lot of complicated procedures, but Eric, it turns out to be one of the fastest sorting techniques in general. And has a good average time complexity. Okay. Now, how about MergeSort? And Eric, if you considered Quicksort to be complicated, MergeSort is going to be way more. Yes, Christian, the return value would be the pivot. Okay, the return value is the pivot around which you're dividing the array into different parts. That's what I wanted to highlight here. Okay, so what was happening here is, remember when you did partition 0, 4, partition A 0, 4 was the first call to Quicksort. When you make a call to partition A 0, 4 using Quicksort, the return value was 0. So that means this number 12, or rather the part of the array containing 12, was divided into one array and the remaining portion was divided into a different array. Is that clear to everyone? Does everyone recall that? We first made a call to partition A 0, 4 and that returned the value 0. Does everyone remember that? See, the return value was 0 for partition A 0, 4. Now what happens because of that is, this part of the array is getting separated and this part of the array is treated separately. Now, when the next call to partition was partition A 1, 14. So this part of the array was getting processed. 11, 8, 7, and 6 was getting processed. When this part of the array, the last 4 numbers were getting processed, what was the return value? The return value was 4. So when the return value is 4, this second half of the array was divided into 2 parts. 11, 8, and 7 were in one part, 6 was in another part. Okay, so every time what is Quicksort doing is it is taking a particular point in the array, dividing that array into 2 parts and ensuring that the upper part of the array is containing elements that are larger than the lower part of the array. So 12 is larger than all the elements in the lower part. 11, 8, and 7 are greater than 6. Is that clear? Okay, so Quicksort ensures that when it is dividing the array into 2 parts, the elements in the upper part of the array are larger than the elements in the lower part. And then it figures out a suitable pivot point where it returns the pivot point, and that's where you divide the array into 2 parts and then continue the processing. Now, for those who thought that Quicksort was difficult, or rather it had a lot of complicated steps, MergeSort has even more. MergeSort seems to be a little bit more complicated, but it's hopefully easier to understand. Let's look at MergeSort. Now, MergeSort divides the array into 2 parts. Each part is separately sorted by making a call to MergeSort. and then the sorted arrays are merged. So here you're not trying to divide the array into parts where the upper part is. So quicksort was ensuring that the upper part is larger than the lower part. But in MergeSort, that's not the way it is done. MergeSort divides the array into two parts. Okay, somewhere in between, approximately in the center. And then it sorts the first half, and then it sorts the second half. Then it merges the two arrays. Is that clear? Is the difference clear? Quicksort, when it is doing the partitioning, while doing the partition, all elements in one half are greater than all elements in the other half. Okay, MergeSort is not like that. MergeSort is okay. So the idea is that merging two sorted arrays is easy. So when you divide an array into two parts, first of all, the problem of sorting becomes easier because you're reducing the problem by half. So MergeSort is making an assumption that by taking an array and dividing that into two parts, what I'm doing is I'm reducing the problem by half. And then merging two sorted arrays. Okay. Quick versus MergeSort. In an average case, Venant, as the name suggests, quicksort is considered to be the faster between merge and quicksort. Okay. So MergeSort is dividing the array into two parts. Each part is separately sorted by making a recursive call to MergeSort, and the sorted arrays are then merged. Okay. Now, because the arrays are sorted, merging can be faster. Okay. Now let's see how this works. MergeSort is calling an array A, and there is a start index and there is an end index. Okay. Now again, you check if start index is less than end index, only then you go into these steps. Otherwise, you don't go into these steps. Okay. The moment you get into these steps, what are you doing here? You're first dividing the array exactly along the center. Start index plus end index divided by 2. So there is a partition index that you're computing. And then you're doing MergeSort, start index, comma, partition index, MergeSort, partition index plus 1 end index. So that means you're dividing the array into two parts. In this line here, you're making a call to the first half and the second half of the array to MergeSort. Okay. Now your assumption is that by the time these two functions will return, by the time lines B and C will return, A will become sorted between the portion start index, comma, partition index, and partition index plus 1, comma, end index. So this particular function call. So let me write this out. Okay. So when you return when this function returns array A will be sorted clear? Is this clear? Is this making sense? Similarly, when this function returns, array A will be sorted between okay. No, not necessarily, Susan. The size does not have to be even. Even if it is an odd size array, it should be fine. Okay. Is this clear? Is this clear to everyone? Yeah, so A, B, C, and D are the, more precisely, B, C, and D are the recursive conditions, with one being the terminating condition. Okay. Now, let's take a look at the merge function here. How does the merge function work? The merge function is creating an array. So when you make a call to merge A, start index, partition index, end index. Okay. So this is merge, start index, partition index, end index. So you have to pass 3 values, which will tell you which is the first half of the array and which is the second half of the array. So these 3 values are telling you which is the first half of the array, which is the second half of the array, which are sorted. Okay. Now the merge function ensures that by making an assumption that the first half and the second half are completely sorted arrays, it combines them together. Now, how does it do that? And someone was saying, can you do it in parallel? Yes, the merge sort can be called in parallel. These can be called in parallel. Okay, but then it becomes a little tricky because you need to be able to access the data in a common fashion and so on. So writing a parallel version would require you to have threads and so on, but it's possible. Okay, so merge length of array 1 is equal to partition index minus start index plus 1. Length of array 2 is equal to end index minus partition index. And we'll work through an example to see how it is. Then you're creating 2 arrays, 2 temporary arrays. Okay. And after creating these 2 temporary arrays, you traverse through these 2 arrays and sort everything together and copy the values into A, into the array A. And we'll see how that is done. Okay. We'll see through an example how that is done. Now, before we go into an example, I think it's going to take us at least 10 to 15 minutes to do the example, whereas we are almost reaching the end of the class. So how many of you need to get to the next class, and should we continue? So if you think we should continue, just click on the green check mark button. We'll need 10 more minutes. If you think you need to move to the next class, just click on the red button. If you think we should continue, just click on the green button. Okay, yeah, most of the people seem to be saying no, we should stop at this point. Okay. Yeah, I can understand. You need to move into the next class as well. But I would urge many of you to go through this. Okay. Honor, please go ahead.
Okay, thank you. I would like to know whether there might be a situation where you see merge sort is the most optimal sorting algorithm you need to use instead of quick sort, or we are always encouraged to use the fastest sorting algorithm.
See, there are cases where merge sort can be better because, for example, if the input to the sorting algorithm, I mean, this is an extreme case, but if the input to a sorting algorithm is an already sorted array, if there is an array which is largely sorted, most of the elements are sorted, then quicksort performs very badly. Whereas merge sort performs much better in that situation. If there is an array where most of the elements are sorted, just a few elements here and there are not sorted, then merge sort is a much better technique than quicksort, just because of the way in which it works.
Okay, does this mean that quick sort can work better in unsorted arrays?
I didn't get the last question. Your voice seems to disappear in between.
Okay, so what now can you hear me?
Yes, yes.
Okay, so I was saying, does this means that quicksort works better for non-sorted element in the algorithms, or?
No, see, both quicksort and merge sort work well. But if you look at the average case, right? If you look at the steps, if you go through the details of the steps, right?
Okay.
What ends up happening is quicksort will do a lot more work if the input array is already sorted. So if the input array is already sorted, does this make sense? So if it is an unsorted array, all the techniques pretty much function in a similar manner. Quicksort is slightly better because the number of steps are lesser. The only exception is if the input array is already sorted, then quicksort performs worse than the other techniques.
Okay. This means that if the inputs of the array are not sorted, means that we are encouraged to use quicksort. It can work better than the merge sort. In case most of the elements are unsorted. Yeah.
Yeah, but then how do you know that the inputs are already sorted or not sorted? So, you need to, it depends on your use case, right? If you already know that it is mostly sorted, then you should go for merge sort.
Okay. Yeah, I get it.
Okay.
Thank you.
Yeah. Okay. Any other questions? Now, those who want to leave, they can leave, and I'll keep on taking questions for the next 10 minutes. And if students have genuine concern about the amount of time it is taking for you to do the assignments, please make sure you let me or the TAs know. But just because the course is tough or because you're already overworked because of other coursework and you just copy assignments from each other, that is not going to excuse you. Okay. You'll have a lot to pay. Any other questions? Yeah, the average time complexity is the same with both quicksort and MergeSort, Fabrice. So I'm going to switch a timer for 2 minutes. If there are no questions in 2 minutes, I'm going to end the class. Those who need to leave, they can take off. Yeah, Honor, go ahead, please.
Okay. Thank you. One of the last questions that I have, I would like to know, in case someone is employed as a software engineer, and then there is a need to apply some of the sorting algorithms. The good way is to try all possible sorting algorithms just to evaluate the time complexity and space complexity, or there is one which would be better that is advised to be used anytime you get a sorting problem.
So
this is
very good question, Honor. Honor is asking, is there any sorting algorithm that that is suitable for all possible situations? That's one question. And I think the second question that he's asking is, if, let's say, as a software engineer, I need to apply a sorting algorithm. Do I try all possible sorting algorithms, try to compute the time complexity and the space complexity, and then pick a method? The short answer, Honor, is you typically, for a given problem, you will be able to figure out which sorting technique to use based on experience. Okay. So, for example, let us say I'm going to give you a situation where the number of elements are not known. Okay. Here, all the sorting techniques that we discussed so far, like quicksort, MergeSort, the insertion sort, and so on, what are they depending on? What is the underlying data structure? Array is the data structure, and they make an assumption that the number of elements are fixed. The total number of elements in the array are fixed, and they don't change as you perform sorting. Okay. Now, when that's the situation, these sorting algorithms are very useful. But there could be a different situation where, you're a software engineer, you are presented with a problem where the data keeps coming in, and you need to be able to sort that data. And the manager might ask you, store only the top 100 values or store only the top 200 values. You don't have to store all the other values. Now, when you get problems like that, you cannot rely on quicksort or MergeSort. You have to rely on other sorting approaches. Okay. You may also have to rely on things like red-black trees or binary trees and so on.
Because the storage might be it's like linked list, because you don't know the size of the
storage will be different, right? So if you don't know the number of elements that are coming in, then you cannot use quicksort or MergeSort. You have to use very different sorting algorithms, and we will study those techniques later on. For now, the techniques that we have studied are techniques which are suitable when the data is fixed. You have a fixed size of data and you want to sort these. So that's where these algorithms are useful. Okay. Christian has asked a question: would creating a temporary array to store sorted elements require more memory but less time? Christian, the answer is, it turns out that it requires more memory, but it does not necessarily reduce the compute time. So, for example, MergeSort uses a temporary array to store the sorted elements. So it takes more memory. but the time complexity is order of n log n. So the time complexity is the same, but it takes a little bit more memory than quicksort. Okay, or even insertion sort and bubble sort and so on. Okay, now packs, is that clear, Christian, first of all? Did you, okay. Now PAX is asking a question, are these sorted algorithms used in scenarios with super huge data? So PAX defines super huge data. What do you mean by super huge data? So if you have big data, right? Again, like when you say big data, what do you actually mean by big data? So this becomes a little tricky. When you say big data, when we say big data, what are we referring to? Okay, one, data that is not numeric. Okay, so you can have data that is not numeric. So if you have string, character array, or even other objects that need to be sorted, how do you deal with this situation? Okay, you will have to deal with this in a very different manner. All right, now here you might have to resort to other techniques like a try data structure or some other methods, even hash. Okay, because the time complexity of doing a comparison on a string might be so big that you just don't want to do it. Like if you're sorting strings, right, string arrays, and you have millions of strings coming in, how are you going to be able to sort all of those? It's going to be extremely difficult to be able to sort those. So you might have to come up with other interesting ways of storing those strings so that you don't end up spending a lot of time doing comparison. Remember, string comparison is expensive. Okay. Now, if you have millions of values, now this is a different problem. Now, if you have millions or billions of values, you need to ask yourself, why do you need to sort? Maybe it is okay. Is this clear, Pax? Venant, very good question. By the time we finish trees, right, tree data structures and red-black data structures, you will be able to answer this question. Okay. Somebody else raised their hands. Somebody else raised their hand. Was there any other question? Okay, I'm again switching on a timer for 2 minutes. If there are no questions within 2 minutes, I will end the class. So in this particular case, in question number 2, you may think Any questions? We have about 30 seconds left for the timer to go. And by the way, we have made a post on assignment number 2 to explain how you can, there are a few hints that we have posted. So please go through those hints and let's discuss them in the next class. Yeah, well, I was extremely disappointed with your performance in assignment number 1, and that probably what influenced me to not give any bonus points today. But there were some questions for which I was very tempted to give bonus points, but I just held myself back. It has been honestly extremely disappointing to see that several people have actually similar code with each other. Is that clear, Eric? Okay, thanks everyone. Have a good time and let's meet on Wednesday. Thank you.